All right, welcome back. I said I'd make a video solving some of these pumping problems, and we're going to take a look at number 20. So this is going to be a challenging problem. It's going to require some different parts. What I want to communicate mostly is the idea behind setting these up. Okay, and so we have our tank that's this kind of maybe up here. I can show you kind of in this picture. We're talking about this tank here, and it's completely full of water. And we need to pump it out, and there's an extra meter spout on the top. And so I've redrawn that down here, and I've indicated a general slice. And the reason we use this slice is because we have to figure out what happens to every bit of water. So the water down in the lower part of the tank travels a different distance than the water up to the top of the tank. And so what we're going to do is we need to know the mass of this slice. And since this problem is in meters, what we want is we want to get maybe, in fact, let me just change mass here to force, because that's going to be what we need when we're doing work. We need to find force and distance. So that's going to be something in newtons. Right? And what we can do is, if we can figure out the mass in kilograms, that's going to be, say, the mass in kilograms times that density of 1,000, times 9.8 meters per second squared. So if we can find the mass of this slice, then we can just multiply by 9.8, and we'll be able to get that work. Okay? And so really what I'm going to be looking for is the mass. And what is that mass? Let me just go ahead and kind of work that down here. The mass of the slice is going to equal the volume times the density of water, right? And so whatever that volume is, that unit is going to be in cubic meters, and the conversion for water is that there are 1,000 kilograms in 1 cubic meter, which we talked about the other day. By the way, I do recommend reading this section very carefully. These problems are hard, and sort of reading the steps in the book for the problems they work out and writing alongside them, I think will be really, really beneficial. Right? And so if we put all of this in here, we need to sort of find the volume of the slice. So write volume down here. We've got to multiply by 1,000 kilograms. And then, let me get rid of the units here. It's going to clutter things up. And so that's going to be our mass that we've just done. And then we need to take that mass and multiply by 9.8. So if I multiply by 9.8, that's going to give me my force. And now if I think about the distance that this slice needs to go to get out of the tank, it's going to be this distance up here. Now I could go ahead and call this x. I've done that in previous examples where that was a really good choice. But for reasons that you'll see in a little bit, I'm actually going to make a different choice of x. And the choice of x that I'm going to pick is I'm just going to talk about x being this distance here from the center of the tank. Right? And then now, of course, to get all the way up to the top of the tank, well, this is a distance of 3 because the sphere has radius 3. And then all the way up to the top of the tank then is going to be 4 meters. Okay. And so with this choice of x, and you'll see why this is a convenient choice in a second, the distance that slice is going to travel is going to be it's going to be 4 plus x. Okay. And so that's going to be our amount. And when I look at the setup here, this is going to be the work for slices below the center line. Okay. And if we think about what x can range from, well, x could be really small. X could be like this distance here, or x could be all the way down to the bottom. And so x is going to be ranging from 0 all the way up to 3. And so what we're imagining here, we're imagining all those little slices, like this one, or this, or another slice over here, maybe down here at the bottom. So we're imagining all those slices that are appearing in the lower half of this tube. Right? So this is going to be the work for slices below the center line. Separately, we're gonna work out the work for slices above the center line. Okay. And so when I work that out, I need to find the volume. And so what is the volume of this slice? Well, I need to know the thickness. And we're always going to think of the thickness as being really, really small. And we denote small quantities by delta x. And so the volume of that slice, well, let's see. I'm going to need to know a little radius. I look at this and I say, oh, well, my radius is definitely changing. So this is going to be my radius. I'll call that r. In fact, let me just erase some of this blue so it's a little bit clearer. Oops. Okay. So I'm going to draw in our radius here. And let's call this radius r. Okay. Okay. So we have a radius r. I'm going to draw this kind of big triangle here. And I need to find the volume of this slice. Well, that volume is going to be equal to pi r squared h, because it's a small cylinder. H is going to be my thickness, delta. And because I've got this little cylinder in here, this little cylinder shape that we're talking about. And now all I need is I need to know that radius. And I'd like to get everything in terms of x. So if I look at this picture, I say, oh, well, this is going to be 3, because that's the distance from my center of my sphere out to the edge. So that's going to be a 3. This distance in here is going to be x. And so by the Pythagorean theorem, I'm going to see that r is equal to the square root of 9 minus x squared. Okay. So I use the Pythagorean theorem there. And so if I work this out, pi times r squared is going to be pi times 9 minus x squared times that thickness, delta x. Okay. So let's put all of this together and see if we can kind of maybe space some of this out. So I need to sort of substitute in for that volume. So why don't I move all of this stuff a little bit off to the right, get rid of these labels for the moment, and substitute in our expression for that volume. So that volume that we just worked out is pi times 9 minus x squared, and then of course that delta x is going to become our dx. So maybe I'll move all this stuff together and put in a dx there. Okay. So this is kind of a not too bad expression. Let's kind of pull things out of it. We could pull out, let's see, 9.8 times 1,000, that's 9,800. We could pull the pi out, times the integral from 0 to 3 of 9 minus x squared times 4 plus x dx. And if I want to kind of work out what that number is, let me just get rid of that. I'm going to move this one down. then to calculate this, let's just use a calculator. All right, so I'm going to switch over to Desmos. I'm going to do the integral, int, from 0 to 3 of, what did we say? 9 minus x squared times the quantity 4 plus x. Close parentheses. Let's write dx. And it's going to give us 92.25. And I think what we needed to do is we needed to multiply by 9,800 times pi. And so at the very end, we get this number here, which I wonder if I can copy. So if I copy that number, I can put that back into my writing. I probably have to type it here. Oop, that didn't work. I don't know where that number is. Let's just remember what that number is. So that number is about 2.8 million. Okay. So that's 2.8 million. Let's write that down, 2.8 million joules, because we're in the metric system. And again, that's going to be how much work it takes to pump out all of the water below that middle line. Okay. And so what happens, what's going to change if we're pumping above that middle line? Well, above that middle line, we're going to have to use a slightly different picture, right? So for work above the middle line, kind of the same type of picture. But now our strips are going to look something like this. Oops, not quite like that. They should be more elliptic. This is my first time trying to use the auto shape feature, and it doesn't seem to be working very well, so I'll just kind of freehand it. So if we have a shape like this, a small disk, then I'm going to use a similar convenient way of labeling this. Let's just draw the strip a little bit smaller, just so it kind of looks like that. So I'm still going to call this distance x, because that's going to be very convenient for me when I draw this triangle. So again, this radius is 3, this distance is x. This distance here will be r, just like it was in our example upstairs. And so if I set everything up, let's just talk about the volume of this slice. So the volume of this slice is going to be pi r squared h. It's going to be pi r squared times delta x. And we have to figure out what r is. Well, again, the Pythagorean theorem is going to tell us that r is equal to, in this case, the square root of 9 minus x squared. And so then our formula for volume is going to be pi times 9 minus x squared times delta x. So we do in fact get the same formula, but note that our description of what x is a little bit different, right? Because now x is the distance kind of above that line. Okay. So that's our formula for volume, and the distance this slice travels. Well, let's see, this slice here, remember it's this slice up here at the top. The slice at the top has to go up this distance here. So how far does that go? Well, I guess this whole distance from here to here is going to be 4. And then this little distance here is going to be x. And so our slice is going to travel a distance of 4 minus x. So this distance is going to be 4 minus x. Okay. So if I put all this together into my integral, so my work integral, again, now might be a good time to pause the video and see if you can put these ingredients together to get the same answer as me. I'm going to do it quickly because we've already done all the steps for the first one. So I'm going to get an integral from, in this case it's going to be 0 to 3 of pi times 9 minus x squared times 4 minus x times the density of water times gravity dx. And when I pull everything out, I'm going to get 9800 pi times this integral of 9 minus x squared times 4 minus x dx. And so I'm going to type that back in, and we're going to actually notice that the integral is very, very similar. So the only difference between the previous one we did and this one is that instead of 4 plus x, we're going to have 4 minus x. And so now we get looks like 1.6 million, right? So I'm not going to be super precise with all the decimals, but this is going to be about 1.6 million joules. Okay. Okay. And now when I add those together, so I'm going to get the total work is equal to, let's see, 2.8 plus 1.6 is equal to 4.4 million joules. So in this case, I chose to set it up in sort of 2 different pieces, just so that my triangles were nice and x was always a positive number. You could think about whether we could just kind of use the first setup, right, up here. And instead of letting x go from 0 to 3, you could imagine letting x go all the way, say, from -3 to 3. And so if you wanted to set that up, you could, and that actually would give you the correct answer in this case. We'll go back and kind of see what that looks like. So if I change it back to my first integral of plus x, and I change that 0 to -3, I do indeed get 4.4 million joules. So, as always, there are different ways to set these problems up. What's most important, again, is to just have a really, really carefully labeled picture. And feel free to leave comments, ask questions about this one. Thanks for watching.